Hello, everyone. Good morning. Good evening.
Good morning.
Hello, everyone.
So welcome, everyone, to the Ntarea working group at IETF 112. So let's start with the virtual etiquette and meeting tips. So as a reminder, please join the queue before participating. Mute your microphone unless you are speaking, and preferably turn off your video. So we are sharing here, Wasim and myself. Hi, everyone. Let's start with the note well. So please remember that by participating to the IETF meeting, you agree to follow the IETF process and policies, that your contribution is covered by patent applications. Then you have to please disclose or notify the chairs about it. Your participation, it's written audio and video photographic records will be recorded, and you agree to respectfully treat other participants. So note on that a brief reminder of key points from RFC 7154 from Guidelines of Conduct. Please extend respect and courtesy to colleagues at all times. You'll remember that the discussions are impersonal and for technical reasons. Our goal here is to devise solutions for the global internet, and that's the main goal of the discussion, not to attack or criticize personal contributions, but to advance the technology together. And please make sure that you are prepared to the discussion by reading the mailing list and the slides beforehand. We are short usually in time, so we try to be brief with the discussions and to the point. Again, remember that minutes are taken. The meeting is being recorded. The presence is logged when you log into the data sheet. And for the scribes, please contribute online minutes to the CodeMD link. For that, do we have a note taker that can help us advance the meeting? Luigi?
I can offer the same service like last time, so I don't type quick, so I will not take notes live right now, but I can prepare minutes afterwards with the recordings, if for you guys is okay.
Lovely, thank you very much. Thanks for that, Luigi. And everyone else, please feel free to contribute also to the notes if you can help Luigi with that. All right, so we have a quite packed agenda. We're going to start reading a quick update on the working group items, moving to SED, two presentations on the lowest address and formal reserved address space. Then the challenging scenarios and gap analysis from GIA. We have then the how you song with a short hierarchical IP addressing, the source address validation by Dan Lee, then the carrier grade minimalist multicast with beer from Thorless, native minimal protocols from Shen Yang, and an update about IEEE 802.1CQ from Roger Marks. Are there any comments or changes to the agenda? All right. So just a quick update for the working group status, as you probably saw on the mailing list, the GUI, generic UDP encapsulation draft, was declared dead in October. If you have any questions about the process, you can see section 426 of RFC 6174. Okay, so that's pretty much it. So maybe we can move to the next presenter. Seth, are you online?
I'm here. Good morning.
Good morning. So nice to meet you. And please feel free to share your screen, your slide.
I sent the slides by email. So if I click Ask to Share Slides, is it available in the... it says no slides available. Should I perhaps do the screen share instead?
You can request again, and then yes, give us a second. It'll be there.
Ah, I see. Thank you. I will say I was looking forward very much to meeting everyone in person in Madrid, and I'm sorry that that wasn't able to happen. But I see that IETF has become extraordinarily experienced with virtual meetings.
Yes, we're having an issue with the screen. Is it possible to you to share your own screen? Okay.
Yes.
Just try that.
And I will... Can you see this?
Yes, now we can see.
Okay. Well, I'll present from here.
Great.
Okay, thank you. Thank you very much, and good morning to everyone, and good other times of the day to everyone, depending on time zone and part of the world. I'm Seth Schoen. I'm here presenting on the IPv4 unicast extensions project. And we have submitted 2 drafts which are up for discussion today. As well, we've uploaded 2 drafts in the same series after the deadline for this Ntarea meeting. And so I'll just preview the other 2 very quickly. But the first 2 on lowest address and 240 are up for discussion in this meeting. So our project is interested in making available large amounts of IPv4 address space that no one is using, that has been historically reserved or dedicated to special uses and has never been allocated. We believe that this can be accomplished with very small, very gradual changes. In many cases, just 1 line or so of code per address category per operating system, providing hundreds of millions of new unicast addresses with billions of dollars of economic value to internet users. And I'd like to note that the largest change that we're going to talk about here, 240, has been default behavior, that is the behavior that we specify, has been the default in many widely used operating systems since a similar change was proposed at IETF in 2008. It's actually quite possible that many or most of you are using devices to view this presentation and to interact with this meeting that already implement the behavior that we specify. In addition, the other changes that we'll talk about are currently default behavior in Linux and FreeBSD systems. So we have fairly widespread implementation of the things that we're specifying here. So as many of you will know, when the internet was first devised, when IPv4 was first specified, it was impossible for people to foresee what a success the internet would become and how it would grow. And for various reasons, large numbers of addresses, in fact, more than 8% of the IPv4 address space was reserved for various purposes and uses between 1981 and 1986. Subsequent experience has shown that many of these address reservations are not being used for anything and are no longer necessary operationally or technically. And the associated addresses are still unused despite the enormous and widely discussed shortage of unicast addresses. So these addresses have tremendous value, and there has been discussion for many years, and people may recall prior discussions at IETF about the prospect of opening up these addresses. And we've been looking at that, researching that, doing tests, writing code, writing specifications. And we've found that it appears quite plausible and quite practical to bring addresses into use. So the first draft that I want to talk about is our unicast lowest address draft. And so in 1983, a famous and important historical TCP/IP implementation, 4.2 BSD at Berkeley, implemented subnet broadcasting at the lowest address of each subnet before there was an internet standard as to which address should be the segment broadcast address. Now, subsequently, the IETF community created a standard specifying broadcast at the highest address of each subnet, and everyone has agreed in all documentation for a long time that the highest address is the consensus broadcast address and the lowest address is only meant for backwards compatibility with the 4.2 BSD behavior. BSD itself changed over to using the highest address for broadcast in 4.3 BSD just 3 years later in 1986. And so various RFCs say we want to maintain backwards compatibility with the historic behavior. This is maintaining backwards compatibility with a particular system which has not been used for decades. Therefore, our draft reclassifies this address for ordinary unicast use so that it can be used to number hosts. Now, this is default behavior as of the present date in Linux and FreeBSD. And this change has large benefits in terms of assignable addressing. They're very widely distributed because they're precisely one assignable address per subnet across the entire internet. And under long-standing internet standards, distant hosts, by which I mean hosts that are not on the same subnet with the newly available address or with a host numbered with it, require no software changes because distant hosts are not permitted to assume where the subnet boundary occurs. Therefore, the distant hosts are already expected to interoperate with this, and indeed, they generally do. All of this is to say that you get the benefit of the one extra address per subnet just by making changes on your own network. Our second draft for discussion today is our unicast 240 draft. This refers to the former Class E, back when we spoke of classful addressing, or experimental range 240/4, from 240 up to 255 as the first octet. This is over 268 million addresses, more than 6% of all of the IPv4 address space. Now, these addresses were reserved for future use in the 1980s. There were many reasons to think that this would be useful, that there would be additional addressing modes other than unicast. For example, Anycast was proposed to use a dedicated address space. There have been IPv6 transition mechanisms that have been proposed to use different address space, and so on. None of the addressing modes that have been proposed have ended up being deployed, and none of them have been able to make use of this space. So there were two proposals presented in 2008 at IETF, which did not advance as drafts in the IETF process, but were favored by implementers at the time and have been widely supported in operating systems since that time. So our draft designates this range as ordinary unicast addresses. And that means a request to implementers to implement the behavior that these are ordinary addresses which can be used to number hosts. Our draft does not say what shall be done with this address space. According to our draft, it remains unallocated, and we save that question for a future day. And I'll discuss in just a minute that we envision this being a gradual process, which involves more involvement from the internet community in testing and assessing the deployment and compatibility questions. Now, as I mentioned, since 2008, most operating systems have supported this addressing range as ordinary unicast, or can easily be configured to do so. And again, many of you are probably watching this very presentation on an operating system that supports this behavior out of the box. This includes popular operating systems like Linux, Android, and Apple's desktop and mobile operating systems. This also works so well that we've seen documentation showing that some cloud vendors are unofficially using this address space as private address space because they know that the particular systems that are going to interact with each other are running operating systems that support it. Just to preview drafts that we uploaded after the deadline, we have a draft on the 0/8 network, which was reserved for an ICMP-based auto-configuration protocol for hosts back in 1981. That protocol was not compatible with Ethernet and was supplanted by auto-configuration protocols like BootP and DHCP. And in 1989, the mechanism for which 0/8 was originally reserved was noted to be obsolete. Nonetheless, the space has remained reserved, even though it's not being used for anything, and modern non-ICMP IPv4 auto-configuration using DHCP uses only one address rather than 16 million addresses. This behavior that we document in that draft is also current default behavior in Linux. And we've uploaded the draft on unreserving most of the 127 IPv4 loopback network. We note that IPv6 has only one loopback address, whereas IPv4, for historical reasons, has over 16 million of them. And we've seen that very little software ever uses or refers to the great majority of these loopback addresses, and does not typically, in fact, use them for loopback. For this behavior, we're not aware of any deployed implementations, and we look forward to discussing both of those drafts in the future. So I want to emphasize that for all of these changes, the behavior changes for implementers are very small. And we know this because we've prepared and tested changes ourselves for various operating systems that implement these behaviors. As I said, some of those are already deployed as default behavior. Typically, for each category of addresses in an operating system, you have to change about one line of code in the operating system kernel, which is typically removing a special case that creates a special case behavior for a particular kind of addresses. And we've noted that for all of these changes, systems whose software has been updated interoperate with one another when numbered with the historically reserved addresses. Now, the process that we propose and the process that we envision is a gradual one. In particular, we propose that these behaviors be recognized as standard and that implementers be asked to implement them in their operating systems. These changes would then roll out gradually in ordinary software updates. And I keep coming back to the proverb that says that the best time to plant a tree is 30 years ago and the second best time is now. By which I mean that we will appreciate in the future having the opportunities to assess the compatibility and the usability of the large number of addresses freed up by these changes. But if we don't begin the process of making these changes, we won't have that choice in the future. So we would like to give the internet community that option in the future, making these addresses usable and then assessing how and when they can be used. So again, our drafts don't allocate these ranges, and that would require future action. And we also note that there have been various cases that the internet community has had experience with, where addresses that were historically unallocated that were widely unreachable have been made reachable through community efforts. And the internet community has successful experience with this. And so a similar process at some point may be undertaken for categories of historically reserved addresses. So to conclude, if we standardize and get implementers to adopt a small number of small patches, we can, with a delay in the future, create billions of dollars of value in making IPv4 addresses available and alleviating IPv4 address scarcity. We've also seen that as many of these behaviors are actually widely deployed around the world and have been for many years, there's incredibly low risk to making most of these changes. Indeed, many of you may be running systems with these changes right now and not even notice. Obviously, the achieving interoperability may be an interesting discussion and an interesting thing for the community to study, but merely having the addresses enabled as unicast is really very, very low risk. So we would appreciate your help in discussing these drafts and helping them to progress. And we appreciate your time very much. These are our email addresses. We look forward to discussion here in the meeting or on the Ntarea working group mailing list. And I'll just leave up a chart that just shows bit masks for the categories of addresses that we're proposing to unreserve, which many of you can certainly envision, but we've just highlighted the number of addresses in each category and the bits that are affected and so on in the IPv4 address structure. Thank you very much.
Thank you very much, Seth. Are there any questions for Seth? We can take a couple right now. Torles?
The presentation. I think it would be very helpful to, add information about use cases where, the current non-endorsed mechanism of, people privately using these addresses aren't good enough, and that would be enabled by doing this endorsement, because, it feels a little bit like fracking, right? So I mean, we've been doing that IPv6 for a very, very long time, and would be really good to see why this investment here from the IETF side to actually endorse, support that, and get involved in all these counteractive changes would be highly beneficial. I'm not saying that I'm completely opposed to it. I think this discussion had been had several times over the past 10 years, but I'd certainly love to see, some really more persuasive evidence of use cases where, simply, going for IPv6 addresses wouldn't be an equivalently good solution.
So I think the fact that there is private use of some of these addresses, we've seen as a good indication, as I mentioned, that the addresses can be unreserved and are in fact usable, that it's a reality that's achievable.
No, I understand that,
yeah.
But why would we need to endorse it if it already works?
So I think the challenge, which has certainly been discussed in the past, is that there are different behaviors of different systems. And while many operating systems do adopt the behaviors that we propose, others don't. And in many cases, the developers of those operating systems have stated when we've talked to them, well, we would prefer to make this change if it were recommended as an official internet standard. In other words, the attitude of implementers to making the changes in advance of an official internet standard varies a lot. Some are quite happy to, and some are quite reluctant to. I think the main use case is numbering hosts in unicast, and we continue to see enormous demand for IPv4 addresses for numbering hosts in unicast. And I see a lot of people in the chat mentioning IPv6, which is certainly a very fundamental thing, right? So I think I've seen about 7 people in the chat mention the question of why people can't use IPv6. And I think this is in a way an empirical observational question, right? That there are lots and lots of networks that continue to want v4 addresses. And one could say, those networks are doing the wrong thing. You know, those networks are improper in some way because they ought to only be using v6. From what we've seen from a lot of people's use cases, they say, we want v4 addresses because if we say our public service is v6 only, an enormous portion of the internet can't reach us. And we've seen in research on IPv6 deployment that many people don't foresee getting rid of dual stack and getting rid of coexistence as something that will happen in the foreseeable future. And I say that not to discourage or criticize IPv6 adoption, but to say IPv4 is still the majority of the internet, and it's still something that enormous numbers of end users continue to use and continue to view as a requirement to use.
Okay, so we have 3 more people on the queue. If you can be brief with your questions, because we're running out of time, please. Jim? Jim, right? You have a question? Jim is probably having issues with his mic. Maybe we can move to Ted for now.
Yeah, so let's see if this works. The issue here, I think, is that you've pretty clearly explained how to solve this problem, right? And that's great, and I think your explanation is fine. But what you haven't explained is why to solve this problem. And what I mean by that is 2 things. One, just as an example, you've mentioned that the 240/ whatever it is being used in private addressing. And so, you know, there's a policy question there. If we were to make it easy to use the 240 plus address space, what would the allocation strategy be for that? Would it remain private use? Would it be public use? We don't have an answer to that. Secondly, there's the question of, you know, whether this is a good idea is actually independent of whether the IETF should be promoting it. So essentially, you're asking the IETF to kind of rubber stamp this idea of you know, prolonging the life of IPv4 through these mechanisms. And prolonging the life of IPv4 through these mechanisms might well be a good thing to do, but that doesn't mean that it's consistent with the with the IETF's mission. So the question is not should you do it, because clearly, as you said, people are doing it. The question is, should the IETF do it? And that's what I don't think you've answered here. You haven't really made a case for why the IETF should do this. What you've made a case for is why users of IPv4 in certain circumstances should do this. That's not to say that you're wrong. I'm just saying that if you wanted to proceed with this, you would really need to make that case. I don't think that this stands alone without you making that case.
Thank you, Ted. So in terms of the private versus public use and so on, the 2008 proposals had one proposing public use of 240 and one proposing private use of 240. And each of those was very specific about how this should be used. And our position is that this is indeed a complex policy question, and that since implementations don't need a different behavior depending on whether the address range is public or private, we want to get started with asking the implementations to go ahead without having to resolve that policy question. And we would agree that people who are using it for private address space might have an opinion about how it should be used or allocated at some point in the future. And I'm certainly seeing an interesting discussion in the comments, and I hope that will continue on the list. But I see a lot of people engaging with the question of what is IETF's relationship toward, we would say, fixing and maintaining IPv4, given that IETF does have a consensus, which we support, that IPv6 ought to be adopted. What does that mean for IETF's work on maintaining IPv4, given that there are also enormous numbers of IPv4 users who are getting enormous value from IPv4, and all analysts believe that that will be the case for a long time to come. And many implementers continue to look to IETF for advice on what to do with IPv4. So to your observation about this might be a good thing and it might not be a good thing for IETF, that may be so, but if so, there's no other entity that has IETF's role and IETF's stature to make recommendations that would be widely or nearly universally followed with regard to the maintenance of protocols like IPv4. And that is a reason that we think that that IETF's statement on this is important, right? We've talked to implementers. We've said to implementers, this is a good idea. Some implementers have said, oh, it looks neat, it looks cool, it looks like some people would like it, but can we get an IETF standard that says that this is the right behavior? So whether or not IETF, and this is an interesting question. I see that, sorry, Juan Carlos, you were perhaps saying that we're running low on time.
Yeah, very, very low. So I think we get the gist of the discussion, and definitely this is something that we will need to take to the list. So I would just, if you don't mind, Seth, let's just hear Bob's point and maybe one quick reply on Ted, but please take this discussion to the list.
Okay, thank you.
Thank you.
Should I go ahead?
Yes, go ahead, Bob. Sorry.
Yeah, just a couple quick things. I manage a couple IPv4 networks, and operationally for me, it would be it would just create a mess if I tried to do any of this, because it's a mixture of hosts and routers from all different vendors, some of which are well known, some of which aren't. And if I start using these addresses and anything stops working, I have sort of an operational support nightmare. I just don't see, this would only be cost for me. And I have no shortage of addresses on any of these networks because I use private v4 addresses, and there's no address shortage. So I don't really understand who this benefits. There clearly isn't. You make a claim that this generates a lot of money. Well, I don't see there's any money here. I think many of your claims are using the words on the slide on the screen is greatly exaggerated. So there may be some value in looking at that Class E space, but in some specific environments for general use, I think this has very little benefit to anyone. Thank you.
Final remark, Ted, or can you take it to the list?
Yeah, just very quickly, I just wanted to reiterate that the IETF, essentially what Seth is asking for is for the IETF to express a policy. And the reason he's asking the IETF to do this is because, as he said, the IETF is a very influential body in expressing policies of this type. And that's exactly why the IETF needs to decide whether the IETF wants to promote this policy. It's not just simply assumed that because the IETF is the place that has the most power to affect this change, that the IETF must therefore affect the change. So that's the argument that you need to make, Seth. And I don't hear you making that argument.
Very much for that presentation, Seth. So we need to move on. So I think it's Dirk.
Yes, thanks everyone. Send request to share the screen if you could. Okay. Good. Slides are up. You can see. Thanks. An update on the internet addressing problem statement and gap analysis drafts. These are 2 slides. I'm combining them into a single presentation splitting the presentation into 2 parts. First, give a recap and updates on the drafts itself, and then feedback from the related side meeting, which took place yesterday after the IETF sessions. And I know that quite a number of you guys attended the side meeting. So on the problem statement, just as a recap, we have a number of example scenarios where the internet addressing, plays a potential issue, a hindrance for internet service provisioning. We have a number of those example categories: constraint devices, dynamically changing topologies, traffic steering, and others that you can find in the problem statement draft. We then also identify the issues that internet addressing may exhibit in those scenarios with respect to efficiency, effectiveness, the complexity, and others. So I urge people to have a look through the draft. We presented this also at the last Ntarea meeting. The gap analysis draft then takes the problem statement further and tries to provide a first round of as the name says, a gap analysis. It first investigates the properties of internet addressing, the fixed address length, the ambiguous address semantic, and the limited address semantic support, and describes those. Investigates the extensions or a number of extensions that patch the addressing properties, and addresses therefore the challenges or some of the challenges that we outlined in the problem draft. The extensions themselves we position in our draft as an explicit proof for potential gaps that have been identified by the community with respect to the identified properties of internet addressing. We also identify that the gaps that were filled by the extensions are done according to the various methodologies that we are describing in the gap analysis draft. We then investigate the gaps that are left by the extensions and some of the issues that are introduced by the extensions themselves, again with respect to complexity, the efficiency, extensibility, that increases complexity, and the fragility for scenarios where multiple extensions may coexist. That's presented in the last section of the gap analysis draft. So what are the updates we made to those 2 drafts? As now problem statement is on version 02. We changed the scenario descriptions so that it focuses more on the problem of internet addressing. There's some wording changes we introduced. We also simplified the problem statement section to be more explicit and more clearly conclude towards the gap analysis that is done in the second document. So they're mainly editorial changes that we introduced in that draft. In the gap analysis itself, we updated the extensions to properties, as we also mentioned in the last IETF meeting, and also simplified the conclusion section to make it more straightforward and clear. So again, hopefully increasing the understandability of the draft mainly, and this is the version 01 that we uploaded. The key part, however, that we worked was to get feedback from the community, and we organized a side meeting yesterday evening, our time, with the purpose to jumpstart a wider discussion that can be carried over to the mailing list. We've seen, and there was an explanation yesterday that Luigi gave in the introduction about the problem of running the IETF online, that we see in some of the discussions a decrease in the actual engagement and the discussion that happened purely over the mailing list, given that the direct social contact during the IETF meetings is missing. So we try to really run this almost like as an experiment, if you will, to describe drafts beyond the actual list to try to jumpstart the discussion. with insights from panelists and the community at large that we invited to join the side meeting. So that's the purpose we had. The focus obviously on the draft, on the problem and the gaps, and whether an architectural approach may help, which is according to the question that we asked both in the problem statement draft and the gap analysis draft. We think that the experiment was to quite an extent successful. We had a huge amount of exchanges. We had 142 messages in the chat that were counted, which probably can give us, weeks or even months of email exchange that we can generate out of this, which is our intention. We're still going through the messages so that we can deflect the discussion back onto the list. The side meetings is not meant to be a permanent institution, if you will, but helps us to generate those discussions. And it was a very, very rich exchange that we believe can really serve the purpose here. So we believe that is successful. It may not scale for every 0-0 draft. So I'm not entirely sure that's a model that you can copy for every new work you want to propose, but we try to at least, for ours, and kind of, we believe it was a very good attempt. A bit on the data, as I said, it happened yesterday at 1800 UTC. We had 64 maximum attendance. There were 61 on WebEx. We also had a YouTube live stream. You can also watch the recording now. We had 3 live stream viewers as well, so 64 in total. We invited a number of panelists. So we contacted Dino, Robert, Michael, Dirk, Nemala, Laurent. Vasilios unfortunately couldn't make it. So I removed him from the list, but we had exchanges with him as well on the various aspects to bring from their perspective into the discussion. After 50 minutes in introduction, we had an open discussion planned for 45 minutes. We ran over 20 minutes. We kept the discussion going because we felt it was a very good discussion, and we didn't want to take the steam out of this discussion very early. So we had more than an hour in total open discussion. The material is uploaded at GitHub. We had from some of the panelists, we had material that we were showing, which is available. But then also now chat, participant list, and all of that you can get at the GitHub under that link, and the actual video as shown here on YouTube if you want to watch the side meeting. So what were the key insights that we found from this side meeting? Well, we had lots of discussion and viewpoints. So the topic seems to be of interest. The number, is not bad. There's about slightly more than half of the people currently in this working group meeting. So that's a good number. And our intention there is the takeaway is to funnel that discussion in the way forward. So utilize the material, the discussions we had, the discussion points, the chat evidences, the statements that we took as notes, and create discussion from this or discussion threads from this on the actual mailing list. That is good. So it served that purpose what we had. But as I said, it also showed that the topic itself seems to be of interest given the rather lively discussion we had. The very key point that was made very early on, there was a lot of discussion around this key point, that there seems to be a larger architectural discussion looming. This is not maybe just about addressing. So revisiting or addressing may just be the outcome of that. And we will continue to drive the addressing discussions with the current drafts, but we will also attempt to capture these larger architectural points in possible future material. That was a very key observation we made from the discussions and from the point that initially was made by Dirk Kutscher in his material. What we are looking into is where to have the discussion, what other outcomes there could be. So stay tuned on that. We're trying to make suggestions on that. If you have suggestions, obviously, we're very happy to hear those. There was also very good discussion around past concepts, and in particular, I found it, to an extent quite daring, but quite interesting that even the OSI model was being brought up, as well as variable length addressing that seemed to have had concepts that made a lot of sense in preventing some of the issues that we have observed also in our drafts, and that people also know generally that we see today in internet addressing. And I think for us, the question is really, can be, which could feed very well into the gap analysis. What are these past concepts that we may want to look again at? Can we tease them out? What are their impacts? What could be their impacts if we would maybe think about some of these past concepts in this new context of revisiting internet addressing? Ultimately, we believe it can enrich the gap analysis draft beyond the currently listed extensions to IP that we currently have. So that's something that we took away as a key insight as well. Another threat, quite clearly, is to not aim at the replacement of IP. That's not the aim. We've also believe we stated that in the problem statement draft already, but evolve IP in the light of existing deployments. So this is not about ripping gear out, throwing it away, and putting new gear in. There was a quite clear thread of discussion around this, particular in the chat as well. That's the fourth key insight that we took away from this. As I mentioned, the chat exchange was quite intensive, which was good, and that was part of the community engagement. The exchanges we saw there, we tried to group them a little bit, and this morning when going through in preparation for this talks, these are the slides, as you can imagine, they really happened after based on the meeting material. On addresses and identifiers, just putting two statements on here around apps having less to do with the network and having less knowledge about addresses from Dino's side. And the idea that URLs help you to find services, and what you want is not where to get it. So you have to redefine what where really means. There was a comment Dino made, and there was quite a number of other statements around addresses and identifiers, which was very rich. There was quite a bit of discussion on privacy. We put these two against each other. They were literally in the chat connected. About the ephemeral nature of EIDs with Dirk Kutcher's response to the extent that you may not actually require them. As well as Robert's point that while security may be concerned with not taking control of a UA, you can't actually really hide that the UA is in the sky over you. So these kind of privacy aspects were discussed in the mail exchange as well. These only as two examples each. Security was another one. About Licia making the point quite clearly that one of the number one challenges in the internet today is probably security rather than speed, right? And apart from the fact that unfortunately packets flow to the 6 big boys, as Dino pointed out, so we are connecting from the security aspect back to an extent to the privacy aspect. There again, more material can be found in the message log on the security aspect, but also another thread of discussion around future use cases. Particularly, what are the features we really would want from the network, as Dino pointed out, and Dirk Kutcher's point on CDNs and hyperscalers as relevant use cases that we maybe could serve better than we currently do. Overall, I said the chat messages are available. These are just pieces we pulled out this morning after a first skim from our side. It's for all to view in the GitHub in all the detail that you can have from the chat messages. We will go through them more thoroughly after also this working group meeting to deflect more discussion, not necessarily even on those fourth threads I already mentioned, but maybe also on others we identify onto the Ntarea list in relation to the addressing discussion. So what's the takeaway we got from all of this? Well, the volume of discussion was very positive. Lots of chat messages, very lively discussion. We ran happily over. People didn't drop off. I think took the overrunning in the stride of the discussion, and we continued, I said it, for about 20 minutes. We found there's enough content of discussion to create follow-on threads on lists. So that was one the purpose of the meeting we had. We will go through the meeting material to create those threads and get them onto the list in order to continue the discussion. We also identified a rich set of contributors having views on addressing and the larger issues, in particular the potential architectural issues. And we're looking into adding contributors as co-authors. So I think there are a number of people that should expect emails and outreach to them to hopefully help us with the discussion as we go forward. And then reflect the community input at large into the revised drafts after this IETF. So we may also look into adding statements similar to the ones I mentioned before as contribution into the revised draft in order to seed material into the actual drafts. Most importantly, contributors are very welcome to join in this effort. So please, if you found the discussion interesting, if you look through the recording because you couldn't make it and you feel that you have something to contribute, please reach out to us. we're very happy to increase the set of contributors to this discussion in order to push this forward. Just to reflect on the hot RFC, you may have seen the video that my colleague Yao made on internet addressing. We're thinking our takeaway from the side meetings, yes, absolutely. Seems to be interested in doing that, so we take that as a positive to move forward. And if you have any questions and comments, happy to do them now. Thank you.
All right. Do we have any questions, especially on the drafts, or any discussion? Otherwise, maybe we can take the feedback to the mailing list to make it part of the Ntarea, and then move to the next presentation. Okay, so next in line is How You. Do you want to share your screen?
So do you have my slides? I uploaded.
Yeah, you can present.
Okay, I try to share my screen. Can you see it?
Yes.
Okay. So hi everyone. Thank you for joining this session. I'm going to talk about the short hierarchical IP address at edge networks. This work is based on a paper we published last year, but we tailored this for the edge network and also interoperation with IPv6. So here's a key motivation for this work. Well, for most of the edge networks, we're talking about IoT networks, and we find the IoT entities, when they communicate, they are very sensitive to overhead and energy. This is because mainly they involve the short message exchange, and many devices are battery powered. They use wireless channel and have a very low storage and computing power. But on the other hand, the IPv6 overhead is very large, majorly due to the address part. And since all these IoT devices in the same edge networks, they pretty much share the same IPv6 prefix. And also most communications could happen just between the adjacent and the related entities. So the question we will ask is that why does this entity need to know its prefix at all? So put the presenter mode. And so that's why if we observe the address they are using, actually for the complete entity IPv6 address, they actually contain several parts. The first part is a common IPv6 subnet prefix they shared. And then below it is we consider that's the entity ID. But if we can further partition the network into multiple hierarchical levels, then we can see the edge network actually contain multiple sections of the address. Only the last part is actually can be considered the entity ID. So this gave me the main idea to improve the header overhead by delegate the network ID and the prefix management, maintenance, and operation to the network gateway routers. By doing so, we allow the entity and node to only know and use its own entity ID. So this way we can save a lot of communication overhead. So left side show a proposal only concerning the addressing part of the packet. By eliminating using the full complete IPv6 address, we just use a variable length source address and destination address. To supporting that, we added two extra fields, the source address length and the destination address length to indicate the length of the address. And for the network, we can see we have a multiple level of the network within a subnetwork. And there are several, some special routers, we call them level gateway routers, actually work against each level boundary for the ingress and egress communication. And in each level network, we also have some other normal intra-level router called ILR. So they do for all the routings within this level network. So here is a more tangible example. In this subnetwork, actually it's just IPv6 subnet. Which is given a 19-bit prefix, which means this subnetwork owns a 32-bit address space. So within it, we can directly allocate end node entities, so which will use a 32-bit network ID, node ID. But we can also further partition this space into some other further subnetworks with a shorter network ID. For example, on the left side, you can see we partition this network into two more levels. And the first level has a 16-bit prefix. And the third level we have further 8-bit prefix. And on the right side, we partition. We have another sub-level network which uses 24 bits prefix. So within this network, you can see, for example, node X and Y are both located in the same level 2 network. If they want to talk to each other, they can directly to use their short address, which is only 2 bytes long. And maybe they only involve the inter-level routers for communication. If two nodes from different subnets want to communicate, they are involved some address operation at the gateway router. For example, you can see the bottom right side, there's example. If the node X want to talk to node N in another network, since they first compare their source and destination address with a different length, so it means they need to go, actually the destination address is longer. It means the packet should go up to the upper level network. So it will be forwarded to the gateway router B first. So at this gateway router, the router will augment the source address with this, the prefix stored in it, which is AAAA in this case. And now the source and the destination address are of the same length, which means they are in the same level of network. Then they will forward in this level. And eventually it will reach the gateway router and of another network, LGRE. So at this point, another thing will be done by the gateway router is to prove the prefix off from the destination address, because it's no longer needed. So now, after the destination address pruning, the packet will enter this network and eventually forward to its destination. So you can see, and any place in the network, the address will be just kept as short as possible. And for interfacing with IPv6 internet, we basically have two modes to support that. First, we maintain a special router. It's just a gateway router. We call it IP protocol translator, because they need to translate the header between the internal format and the IPv6 format. The operation is also very similar to the gateway routers. It's if the packet need to enter the internet, we'll attach the source prefix. If the packet will go into the edge network, will prune the destination prefix. And another mode is we support we can support a NAT gateway at this point. So we can allocate one or more public IP addresses to each edge network. By doing this, the advantage is that the internal address could have arbitrary length. It doesn't necessarily to be limited by the allocated address space. So the benefit of scheme that is first is totally interoperable with the current internet, and it have a significant header overhead saving from 60% to up to 70%. We can further, based on this, we can have some further compression on other IPv6 header fields. By doing that, we can save even more. And this actually simplify both control plane and the data plane, because we enforce a strict hierarchical network architecture at the edge. So we can have a better address aggregation and a simpler router design, smaller forwarding table. So we have done the P4-based prototype and evaluate, and it show it's a very promising. And another key benefit is incrementally deployable, because it's totally transparent to the external internet, and you can basically implement this in each edge network individually. It can still work within to communicate with any entities in the internet. Another key issue is we want to compare this with some other header compression schemes proposed by 6LoWPAN and LP1 working groups. The first is SHIP. We call this our scheme SHIP. SHIP is a hierarchical and extending from edge to core. Also, the scheme is applicable to all kinds of network, but the other proposals may be limited to some specific network environment. And also, SHIP is applicable to arbitrary network topology, unlike the other header compression schemes may only applicable on the point-to-point channel only. And also, they need to compress the packet, decompress the packet before routing the packet, because otherwise they won't recognize what it is. And also, our scheme only considers IP addresses. So therefore, it's orthogonal to the other compression scheme. If we really want to use those schemes, we can still apply them, but with some new benefits introduced by the shorter addresses. And also, SHIP is stateless in a sense. It doesn't need to maintain any dynamic or static context between the peers for communication. Therefore, we don't need to do the compression, decompression, and don't need to store the context. So which actually save the storage and the computing capability of the system. Also, we allow the communication between any internet addressable nodes, which means within a network, the nodes can directly talk to each other. It doesn't need to go to some central point as a proxy. So this pretty much is what I have today, and we welcome collaboration any future work suggestions. Also, we want to get suggestions to find the best working group to adopt this work. Thank you very much. Any questions?
Thank you very much. Stuart?
Yes. What you described sounds an awful lot like 6-LoWPAN header compression or other forms of header compression, which are already in use in millions of products worldwide. You had a slide, I don't know what number because you didn't have numbers on the slides, but one of the unnumbered slides talked about comparisons between SHIP and 6-LoWPAN. That was what the title said, but it didn't actually have any comparisons. It was just a list of claims about SHIP. So I think if you want to make a compelling case for this, you need to make that comparison chart that show how this new idea compares with the thing that is already widely deployed and successful.
Yes, thank you for the suggestion. Yeah, in the next revision, I plan to add this comparison. Yeah, thank you.
Okay, thanks. Dave?
Put this into the chat, but in terms of your last bullet, I think was something like find the best place to adopt the work or some phrasing like that. And I just wanted to say that I think the best place for this discussion is in the 6-Low working group, right, which does more than just the header compression scheme that you're talking about, right? They do over any particular link type. And so there's multiple different link types there, not just 802.15 that was on your slide. And so I think that's probably where the right expertise is, because that's the group that reviews, you know, compression, eliding various fields and various formats and short addresses and all that kind of stuff is in scope for that. So my recommendation is that this proposal just gets dispatched over to the 6-Low working group to evaluate.
All right. Ted?
This is has the author looked at Thread, because I think they do something fairly similar in terms of the way they do routing, and it would be worthwhile to make sure that there isn't some, you know, reinvention of the wheel going on here. Of course, Thread is not an IETF protocol, so there's that whole issue. But at the very least, I think it would be worth investigating whether there is overlap there.
All right. Stuart, do you have a question, or was that from the previous? I guess.
From previous, I always forget I have to manually click lower. I'm sorry about that.
Yeah, no problem. All right. Thank you very much, everyone. So we can move to Dan Lee.
Hello, can you hear me?
We can hear you. You can try again to share your screen.
I'm trying to ask you to share slides.
Okay. We're approving. Just give it a couple of seconds.
Oh, I cannot choose a deck to share.
Just wait a second. See. You can request to share your screen and then just give it a couple of seconds.
Okay, I can share my screen.
Yes. Just wait a second. Yep.
Can you see my screen? Okay. Hello, everyone. I'm Lan Chengqin from Tsinghua University. I'm going to present our draft source address validation, use cases, and gap analysis. The traditional internet architecture lacks the validation of a packet source address. A sender can forge the source address when sending packets, which is also known as source address spoofing. With source address spoofing, attackers can carry various attacks, such as reflective DDoS. So, source address validation SAVE is necessary. Mutually agreed nodes for routing security manners is calling on network operators to implement SAVE. However, it's difficult to solve the source address spoofing problem at a single level or through a single SAVE mechanism. First, it's unrealistic to require a same SAVE to be accepted by all networks. Second, the failure of a single SAVE mechanism will completely disable SAVE. Therefore, source address validation architecture SAVA divides SAVE into 3 checking levels, and Manners also follows this architecture. They are access network SAVE, intra-AS SAVE, and inter-AS SAVE. There are many SAVE mechanisms for different checking levels. For the access network SAVE, SAVE was proposed to force each host to use legitimate source address. Although it provides a host-level validation, it's fully effective only when deployed by all access networks. It's difficult to require all access networks to deploy SAVE simultaneously, so intra-AS SAVE and inter-AS SAVE are more encouraged by Manners. The left figure shows the use cases of intra-AS and inter-AS SAVE. The 4 ACs belong to the same customer code, and AS1 is the start AS. The topology of AS2 is presented while other ACs' inner structures are hidden for brevity. P1 is the source address prefix of router 3. P1 apostrophe is the spoofed P1 by router 2. P1 double apostrophe is the spoofed P1 by routers in AS3. Intra-AS SAVE avoids source address spoofing from inner AS. Router 1 and router 4 should drop the packet with P1 apostrophe from router 2, while accept the packet with P1 from router 3. For inter-AS SAVE, it aims to avoid spoofing from external ACs. AS1 and AS4 should drop the packet with P1 double apostrophe from AS3, while accept the packet with P1 from AS2. RFC 8704 summarizes the recommendations concerning SAVE mechanisms. For intra-AS SAVE, ACL-based SAVE and strict UIPF are recommended. ACL-based SAVE configures matching rules to specify which source prefixes are acceptable, but it requires manual configurations to update. Strict UIPF takes the source address as a destination address to look up the FIB and requires the forwarding interface of the FIB matches the incoming interface of the packet. For inter-AS SAVE, EFP UIPF is recommended to be deployed at customer interfaces. It maintains a RPF list at each customer interface, while loose UIPF is recommended to be deployed at provider and peer interfaces. It only requires the source address appears in the FIB. However, existing inter and inter-AS safe mechanisms have inherent false positive or false negative problems. Strict URPF exhibits false positive in the case of router asymmetry. The left figure shows an example. The access network owns a prefix. Due to traffic policy, it splits the prefix into two sub-prefixes. It advertises one sub-prefix to router 1 and the other to router 2. When router 3 forwards packets to 10.1.0.0/16, the forwarding path is router 3, router 4, router 2, and access network. The reverse path is access network, router 1, and router 3. In this case, when router 3 runs strict URPF, the safe rule is packets with source addresses of 10.1.0.0/16 must arrive from router 4. Therefore, the reverse data flow will be dropped. In general, existing intra-AS safe mechanism has false positive problems. For inter-AS safe mechanisms, EFP URPF and loose URPF have inherent false negative problems. We take AS4 as an example. AS5 is its provider and AS3 is its peer. AS1 and AS2 are its customers. When AS4 runs EFP URPF at customer interfaces, the safe rule is packets with source addresses belonging to AS4's customer coin can arrive from every customer, so aces in AS4's customer coin can forge each other. When AS4 runs loose URPF at provider and peer interfaces, the safe rule is packets with any source addresses existing in FIB can arrive from every provider or peer. So aces outside AS4's customer coin can forge any source address in FIB. In general, existing inter-AS safe mechanisms have false negative problems. An ideal safe mechanism should guarantee accuracy because false positives cause traffic disruption, while false negatives give attackers the freedom to forge source addresses. However, as aforementioned, existing safe mechanisms cannot guarantee accuracy. Intra-AS safe mechanisms have false positive problems, and inter-AS safe mechanisms have false negative problems. The root cause of their inaccuracy is that they all achieve safe based on local FIB or RIB information, which may not match the real data forwarding path from other sources. In order to avoid false positives and reduce false negatives as much as possible, safe should follow the real data forwarding path. To this end, a path probing method can be taken. That is, the source router sends probing packets carrying source information. Then each intermediate router can generate safe rules based on source information and incoming interface. More specifically, when interfaces cannot learn complete forwarding information, a combination of alarm list and block list can improve the accuracy. Besides, designing a practical probing method needs to consider many practical issues, such as high scalability. The design should not induce much overhead and high deployability. The design should generate safe table automatically and support incremental deployment. And high security. The design should guarantee the integrity of each probing packet. So where to promote our work? We have 3 candidates. One is Ntarea, since Sava and Savi are adopted by Ntarea, or RTG, because intra-AS and inter-AS are related to routing, or OPSEC, since EFP-URPF is adopted by OPSEC, or others. We sincerely solicit comments to refine the draft and seek collaborators. Thanks. Any question or comment?
Eric?
Yes.
Working group is the best one. I think for this OPSEC, operational security, is most probably the best one. I know that Jen is in the participants of this meeting. So Jen, as you are the co-chair of OPSEC, if not mistaken, you may want to say a few words on this.
Jen, we cannot hear you.
OPSEC is not meeting this area, but wow. But yeah, please drop the chairs an email, yeah, and we can put you on agenda for the next meeting.
Thank you. I didn't hear clear.
Great. Thank you very much. So if there are no more questions, then we can move to Torrens. You can either share your screen or use the slides. Okay.
Hi. Yeah. Oh no, wait a second. That's the wrong slides. Oops. I don't see my slides uploaded.
Okay. Do you want to share your screen? I think we uploaded it. You sent us just before the meeting.
All right. I hope the slides are showing up.
We can see them.
Okay. All right. So a mouthful of a title. So I wanted to present this. I wrote this draft on behalf of a design from a team of colleagues because it is, you know, a really great evolution of BRTE, in my opinion. Why going to Ntarea? Well, so I think what I wanted like to explain here is what I think is a great example of a story on more intelligent variable length addressing helps to solve, you know, problems that we're currently working on in a better fashion. Yeah, so I hope Ntarea is not for unicast only. Obviously, the target group for this would be beer, but I wanted to, you know, show it from the addressing perspective. So what's wrong with BRTE? That's a great question to ask when you have a draft in ISG review. But it is, you know, in my opinion, the best multicast forwarding solution for the constraints it was defined against, and that is that we wanted to add path steering to the beer multicast solution, which is stateless, and we wanted to keep pretty much everything in the forwarding plane that we defined with BRTE, and so try to make only the minimum necessary changes in the forwarding plane to enable the traffic steering. And so in that respect, it's a little bit similar from how we did traffic engineering in MPLS after we had the non-traffic engineering forwarding solution. But this comes at quite a good amount of undesirable limitation complexities, which I saw especially working through the BRTE draft, and that is that by representing the forwarding through a flat fixed size bit string of pre-configurable length, you're getting yourself into a lot of limitations. The number of bits is also split between the receiver nodes and the topology nodes, so to speak. So without going into a lot of details of something about BRTE that many people here may not know because they haven't looked at it, what we've pretty much done is we have started with a fixed forwarding plane design and ended up with a lot of additional controller operational complexity, less traffic efficiency, but yeah, we got the forwarding plane simplicity of what we've started with BIR. So now let's see what we can do better if we think that we can build a more flexible forwarding plane functionality. The goal, and that's kind of the first part of the name, is to really come up ultimately with a solution that supports multicast in, for example, service provider or industrial large-scale networks in a more simple fashion than current IP multicast, with all the good traffic engineering, what we want, the traffic steering, and then of course there is correlated QS and other things. So it's a controller-based design, and this is just I'm going to skip further details. So here's basically the addressing structure that we're calling recursive bit string structure. And what it really is a representation of the desired delivery tree, where for every node you have a bit string of pretty much the bit string itself is just the sequence of adjacencies, meaning neighbors that that particular router has, 1 bit for each, and the bit string in the packet has the bits set to the neighbors where packets need to be sent to. And then for each of the bits that are going to an adjacent router, there is another recursive unit that is starting with a bit string, and then again, of course, with the recursive units to that, neighbors again. So the fields that we need for that, obviously, is some starting fields that tell the total length of the address structure, and then the length of all the recursive units after the bit string. And of course, each recursive unit itself has, again, the same structural elements. So here is, without trying to walk through it in full and glory detail, the example that is also in the draft, and that shows how you're starting out with a packet originated by client 1, which has such a recursive bit string address. And when you then see what happens on router R, then you'll see that when it's being, on router B, when it's forwarded to router R, you already see that you're forwarding only the extracted part of the recursive bit string address, which is the recursive bit string address for B. And B, of course, does the same thing, to R, and R does the same thing, forwarding to S and E. So the further the packet progresses through the delivery tree, the smaller the address becomes. So what type of simplification performance enhancement do we get through all of this, right? So first of all, we forgo the whole forwarding aspects that we needed to do loop prevention, because by the address becoming shorter and shorter, we're having an equivalent of clearing bits to avoid those loops. There is, and that's, I think, one of the biggest problems that we have in BRTE, but also to a lesser extent in BIR. There is no need to split up the whole topology into subsets of the topology to fit all the adjacencies and end nodes into a fixed size bit string of n bits, where the whole topology would maybe need 20 times n, right? And that also means for BRTE then that the need to minimize the number of bits for the topology to represent it goes away. So there are a lot of things like LAN bits and point-to-point bits. So those are all operational semantics that an operator or a controller could invent to optimize this, and this all has to be documented. It is documented in BRTE. And so especially for sparse distributions, right, for trees with a limited number of receivers, this is very easy. You can always create just a single packet to deliver to any subset of receivers, which is never possible in a large-scale BEER or BRTE network. Yeah, so even when you do need to send multiple packets because the total size of the address would become too large, it's very easy for a controller to do that with a very simple algorithm, whereas optimizing upfront for these cases in BEER and BRTE is much more difficult. So obviously, I'm not going to walk through the pseudocode. Maybe I have more time in the BEER working group, but same type of representation that we have done as a type of informal normative description of how the forwarding would work. But the forwarding plane complexity here, and that's obviously now the interesting part to compare for all the benefits that we get. The basic bit string replication is exactly the same as BRTE, with just a much simpler subset of different type of adjacency required. So the main added work is really that for each of the replicating adjacencies, you need to have the calculations to find the offset and the length of the recursive unit in the address, extract that, and make that become the new address. This is also a naturally variable length address, right? So BEER packet format does support different lengths, but they all have to be pre-configured and operator-wise decided upon, whereas here in this case, you would naturally use just as many bits as you need for a distribution tree, and would only need to configure maybe a network-wide maximum that you want to be able to support. So of course, what needs to be done more is a stochastical analysis and comparison of the efficiencies, the number of copies, header size, and so with this solution compared to BEER and BRTE. That's obviously wide space to explore based on the interesting use cases. The draft, like the original BEER and BRTE architecture, doesn't discuss packet encoding, could equally use the existing packet encoding, which obviously would be a waste because it's a fixed length then that needs to be indicated. But otherwise, it would be perfectly fine. It would just be another forwarding mode of which we would today already have two, namely BEER and BRTE. Right, and that's it.
Thank you. Do we have any questions? Dave, you have a question?
Understanding. I think I followed your presentation, but just to check, please confirm that your primary use case is where the addresses that you're talking about would be constructed by a router and used to encapsulate multicast addresses over the top. Because the question I was going to ask is, how do you learn what address you should send to? And I'm guessing that's because you're using routing protocols to have all the knowledge necessary to construct that. Did I follow it right, or am I off?
Yeah, so the current initial use case of BEER is that you put it on the PE routers as a start, ingress and egress PE, and you do a mapping between the IP multicast overlay and BEER. And that obviously is a great way for service providers to optimize their network, but it eliminates for the application one of the cool core benefits of all the beer solutions, which is that an application sender can by itself determine which receivers each individual packet goes to, as opposed to having to deal with the bloody multicast groups and setting them up. So that's why its simplification would be to extend beer all the way to the hosts, which isn't architecturally a problem, but which is a problem of is that something you today can scale? And with this solution, I think it's a lot easier to scale this for applications than it is with the existing beer TE.
Thanks. Are there any other questions? Okay, thank you. So then we move to Shenzhen.
Can you hear me? And can you see my screen?
We can hear you. We can still not see your screen.
Did my screen start?
Not yet.
Hold on a
You can also
second.
use
It's on my
preloaded
side. Sorry, I forgot. I didn't click the confirmation button. Sorry, my fault.
Okay.
Here we are, I believe. Can you see it now?
We can see them.
Can you see it? Okay, so here we are. This what we call the native minimal protocol is a new proposal for the flex edge network. The purpose is to extend the IP wider into many non-IP networks, which is widely deployed at this moment, such as ZigBee, Bluetooth, CAN bus, Modbus, and etc. There are many where for nowadays, because IP is heavy for energy-sensitive devices in this network. For they actually need the application layer gateways to transfer their connectivity into the IP, then can connect to the other servers in the IP networks. And also they cannot communication between the different non-IP technologies, even they are in the same edge network. And there are three main issues for this. It's not support the end-to-end security, IP layer security, also the TLS. And those non-IP terminals are invisible to the TCP/IP networks, and the servers cannot see them either. The servers only see the delegate from the gateway. And the dynamic joining and leaving for those devices to IP network is complicated. Of course, people we would like to bring these sensors devices into IP. The answer would obviously be IPv6 consideration first, but actually it's not suitable. It's cased by the LAN address and header.
Sorry, Sheng, we are seeing your slide number 1. I don't know if you are moving.
I'm moving to the number 2.
We see number
problem
1
here?
now. Okay, now we see number 2.
So now you see the second slide.
Correct.
Can you? Okay. So let me continue. I'm at the bottom of this page. The IPv6 is not suitable because the actually this non-addresses and the header 40 bytes in total, not including the options extension headers that consume more energies and times both on terminals and network transmission. 6-node and 6-node PAN actually has done great job to compress the header, including the address, to save the energy for the network transmission. But actually, it puts the terminals burden even heavier. So now we actually has more problem for the resource constrained end devices. They are short of both energy and memory. So this proposal is for them. I move to the third slide. Can you see that? Okay, I continue. So what's the this new proposal native minimum protocol? It's a simplest protocol with native short addresses that's we particularly designed for the edge network with those resource constrained devices. The address lengths are mainly 6 bits or 8 bits or 6 bits. It's extensible, but for most of works, 1 byte or 2 bytes, that's enough. And we have the minimized header with the short addresses. And we design very simple signal messages. This new protocol supports communication between terminal and gateway, also between terminals with the same edge network through the gateway transfer. The functionalities we have, including the header design for both data packet and the control message. And we also have very simple address allocation and management mechanisms. We also provide the DNS delegation services. When these terminals need to communicate with the IP network, it's transferred, it's translated by the network, by the gateway. Gateway actually translates the package into the native IPv4 and IPv6 packet, but that's purely layer 3 translation. That's different from the non-IP to IP. The information within the package can be matched. This is the data packet header. It's designed with the bitmap mechanism. For now, we have the most frequently used 6 fields encoded in 1 byte bitmap. More fields can be supported by extend the bitmap. For now, we have only destination, source, next header, payload length, checksum, DNS indicator. This is an example. It's typically the header has only 5 bytes, and it can be even shorter to 4 bytes without the source address because the gateway already know who sent this package to it. And this is the address management functions design. All nodes in the same network use the same address length. 8 bytes, 16 bytes is configured on the gateway. And we have the address allocation through the address request and address assignment messages. We have the least reversal challenge and the least reversal response message to manage the address lifetime. This is a design for the control message body format. Very simple, straightforward. This is for now the only service we provide because most of those terminals may request the DNS. How to do it in the minimal protocol? The AMP terminals send a DNS request package to the gateway. When the gateway receives the packet, it directly translates the network layer information, the DNS request, and send a regular DNS package, request package to the DNS server, which configured earlier on the gateway. Then get the DNS return information back. The returned DNS message is encoded in the return data package towards the source terminal. So DNS lookup can be completed. Some consideration for security, we actually have shorter checksum from 16 bits cut into 8 bits. It costs less bits and computation. We do have a little bit loose here. It increases the possibility that the checksum is bit error during the transmission. But nowadays, the transmission is more trustable. And this proposal lead consideration. We did the user type, new user type, and we did the registration for the AMP control message type and the bitmap table. Okay, that's it. This is the first time we show this, and we think that's very useful. So I would like to hear response, how to improve, whether this is useful, even whether we need to make it even simpler, which we think that's almost impossible. This is the simplest one for
Thank
the
you.
edge network. Thanks.
We're out of time, so we will have one question. Dave, do you want to make a comment quick?
Sure, I'll just make the same comment that I made on a previous presentation in here, which is I think this one is best reviewed in the 6LoW working group. For example, I think the claim that is on slide 2 or so, that 6LoW requires terminals burdens to get even heavier, is something that I think that they should address. Whether that's correct or not, I don't know. But if it is correct, then that's something the 6LoW working group should take as feedback. But either way, I think the types of things that you're evaluating here, especially since it's a gateway that does translation, with 6LoW. So that's where I would review this work and encourage you to go and present this there. And I think it'd be a great discussion. So thank you.
All right.
Yes.
Thank you very much.
Yeah, we would present there.
Great. Thank you, Sheng. So we are going to move to Roger.
Let me share my screen.
Yes, that's granted.
And
we can see it now.
Okay. Okay, thanks, Juan Carlos. So my name is Roger Marks, and I want to talk about an IEEE 802 project, standardization project called 802.1CQ on address assignment. This has been discussed in the IETF 802 coordination activity, and recently I was asked to bring this presentation to update Ntarea. So this is a project that's been around for a few years, but it's gotten a slow start, and now it's starting to move more quickly with some drafts. It's about multicast and local address assignment of IEEE 802 addresses, or what you might call MAC addresses. It's done in the 802.1 working group in the TSN time-sensitive networking task group. The project charter for this activity specifies that it's on local addresses, and it should support both peer-to-peer address claiming and address server capabilities. And the intention is to consider the fact that global addresses could eventually be exhausted in the 802 space, and there should be a way to promote the use of the local address space and provide locally unique addresses. An additional burden that's placed on this project is to deal with the multicast addresses, and the it's a little different than what people always expect, because many people are familiar with the idea that a multicast address is assigned to a protocol. but in this project, the multicast addresses need to be assigned to N stations. This is driven partly by the idea that in some TSN networks, streams are addressed to multicast addresses, and those are assigned by the sender or the talker. And so each stream and its set of addresses uses a different, and its destinations is decided by the sender, and it needs a pool of multicast addresses that it can use for that purpose. Currently, there's an IEEE standard 1722 that provides a peer-to-peer way for devices to get these multicast addresses, but this would provide new capability. 802.1q would give new capability in addition to providing the local addresses. So it's important to understand that half of the 802 addresses are global, and those are by a rule required to be unique among all devices, and the intention is to have that uniqueness go over a period of 100 years. And we're well into the 100 years, and there's still addresses left, but we're worried about them being exhausted. And these are generally burned in by the factory, and so these are flat addresses. Their only real purpose is, and the only content in the address is its uniqueness, along with an indication of whether it's global or local, and whether it's unicast or multicast. But half of the 802 addresses are local, and it's possible to assign those dynamically. And there are many, many addresses here because the size of the global space and local space are equal. So you can assign these addresses very liberally, but also because you're doing them dynamically, you can assign them thoughtfully to have addressing power where there's content in the address rather than just uniqueness in the address. So what happens in 802.1q is called the Block Address Registration and Claiming Protocol, BARC. And BARC assigns MAC addresses in blocks, where an address block is a set of local addresses that's equally unicast and multicast, each contiguous sub-blocks. And these are all distinct disjoint address blocks. And there are two types. There can be registrable address blocks that are handed out by a registrar, which is a kind of a server that holds blocks, inventories of address blocks. And then there's also claimable addresses, or CAs, that are in claimable address blocks, or CABs that are each identified by a CABA, which is a claimable address. And the CABA is a MAC address that's a multicast address that's used as an identifier. And there's a number of temporary unicast addresses that are used for initial discovery by a claimant that doesn't have a burned-in unicast address, say, from the factory. So this figure tries to show a little sketch of these addresses. So this is showing 12 nibbles that's part of an 802 48-bit MAC address. And up in the header, you can see there's this bit M, which is the well-known multicast bit, 1 or 0, depending on whether it's unicast or multicast. And then the purple, the second bit here in N1 is the indicator of a local address. And so in BARC, you always have use a 111 for these 3 bits, and the M is unicast or multicast. But we also structure in BARC that the first part of the first nibble, and I want to call your attention to these 2 green bits, J and K, because those are the ones that tell you the size of the address block. And so it tells you how many addresses that you get in your address block. So you get 16, the block has 16 to the JK claimable addresses, or 16 to the JK registrable addresses, depending upon which one you use. So here's an example of what the claimable address blocks look like. And it shows 3 sizes, 0, 1, 2, and 3. And the size 0 block is, it has this header at the top in the first 3 nibbles, and then it leaves you 9 more nibbles to assign an address. And because there's an asterisk here, that means that you can have a local, you can have a unicast address and a multicast. So your block is 1 unicast and 1 multicast address. But if you go to the larger sizes, you can have, for example, 3 nibbles worth of address space. And so now you're giving an address block that has 4,096 unicast addresses, equal number of multicast addresses in this cab, that's the address block. And then this CABA is the identifier of the address block, and it's a multicast address itself. And so the way you do claiming is, here's an example where you have 5 devices that each hold a CABA address block, 1, 2, 3, 4, 5. And here's a new one that wants to claim an address, so a block. So it picks CABA 1 and it sends a multicast message addressed to the multicast address CABA 1. Well, it turns out that because it's a multicast address, the only device that's listening for that address is the one that holds the same claim. And so these 4 of these devices don't even listen to the message, but the one that holds exactly that same block that's being claimed hears the message, and it responds with a unicast message to the claimant saying, no, you can't have that address, I've already got, you can't have that block, I've already got it. So it tries again with a different address, 6, this time nobody responds because nobody hears that message, and then it decides to claim CABA 6. This can also, the registration process is such the claimant doesn't have to be aware that there's a registrar available when it begins the claim. It sends the same claim message, but if there's a registrar, it can respond and provide an address. So in this case, the claimant sends a discover message, and let's say there are 2 registrars out there that each respond with an offer to the claimant by unicast, and then the claimant picks the one that it likes and it sends a unicast message to that registrar, and it reserves that address. One of the things that you can do with this kind of structure, it's because it's in blocks, you can do a kind of a hierarchical structure, and there's some techniques that are available within the standard. This structure is my example. It's not standardized, but it's to show that you can have a kind of a semantic structure. So an address can have a field that tells you how the address is formatted, and then within it you can have code the address to say, okay, here's the access switch that it's in, and then maybe here's the server that it's attached to, and then here's a virtual machine that's on the server, and you can have routing methods that take advantage of that hierarchy. So what you end up with is a general address assignment method that can eliminate the need for global addresses and reduce the consumption. It still maintains uniqueness within the LAN. It's completely backward compatible with existing 802 addressing and bridging, because it's just for a device that just sees it as a flat address, it works the same as a global address. It could be used to address privacy concerns because the addresses are dynamically assigned and they don't continue. And you can use some semantic structuring, including, because a device, you can grant a device a whole block of addresses. It can use the free fields to do things like flow identification or identify streams within the core address block that it's been given. You could scale this up, and you can use it in hyperscale class networks. And it's an alternative to completely random assignment. Like, for example, in the wireless case, you have a dynamic assignment possibility that can give you address privacy, and meanwhile, we're protecting in the protocol against address duplication, and you can code the address blocks. It's also possible to use this to consider how you do 48-bit bridge LANs to carry 64-bit addresses. What needs to be explored is the implications on IP, and you could think about ARP and how ARP applies in this case. And the intention is for the next draft of this standard to be circulated to Ntarea, and hopefully that will happen. And maybe within the next couple of months, a month or two, there'll be a new draft circulated to Ntarea.
Great. Thank you very much, Roger. So we're very much at the end, but we can still take a couple of questions if you have for Roger. Eric?
But more about, thank you for coming. I'm quite happy to see that IEEE engineers are coming to present their work the Ntarea. That's very useful to get this collaboration between IETF and IEEE. So thank you for coming.
You're welcome.
Thanks, Eric. Torles?
Yeah, I mean, this is interesting. Thank you. We obviously have a lot of experience with things like that from multicast at layer 3 as well. So I think one of the big issues of this is how you ensure that the applications are going to deal with the unexpected loss of an assigned block. If you had a network partitioning and then partitions merge, you have duplicate allocation of the same block, which you would need to trigger up to the applications. You need a decision mechanism. Who of the two allocators loses the block? And so, yeah, I very much appreciate these fully distributed algorithms, but be sure that you really walk through all the problems.
Well, we do have a lot of that covered in the draft, and hopefully when we circulate the draft, you'll have a chance to take a look at that.
Yeah, but again, I think the problem is, the understanding of the implications going up to the application level, right? So I think that's what you always need to worry. Will you be able to have the enforcement, the verification, the validation tools that applications really behave benignly under this circumstance? Because something that is rare is for, especially if you go into industrial or any other type of highly resilient application environments, you need to think about test suites or other mechanisms.
All right. So thank you very much, Roger. So then I guess we expect to see some feedback from the IEEE and get the draft circulated in Ntarea. Roger?
Sorry, what's the question?
No, I'm just saying that then we will see the draft being circulated and.
Yeah, hopefully within a month or two we'll have it, and we're already preparing a draft statement to provide it, to pass it over.
Perfect. Thank you very much. So for those interested, I guess we will see a link on the mailing list about this. So we're at the end, and thanks everyone for attending the Ntarea. Hope you have a good end of day and follow-up meeting. So good flight, Wasim. Take care. Bye-bye, everyone.